for this invitation. I'm really very glad to come here, especially in this room where I learned a lot of mathematics 30 years ago, like, for example, complex analysis and things like that. So I'm always very glad to give a talk here. And so I think it's working. Okay, well. So today I would like to present the so-called networks of chemical reactions. And I think that since we have 3 sessions, the first one will be mainly devoted to the, let's say, existence and smoothness theory for the equations coming out of those networks. And then the 2 next sessions, tomorrow and Wednesday, will be more focused on the large time behavior and which be much closer, let's say, to statistical physics. This session will be, let's say, using more PDE theory in some sense. So let me present, actually only with examples, well, we'll start here. These so-called networks of chemical equations or chemical reactions. And before giving some kind of definition, I want to present 2 specific examples, which are the examples which will be treated during those 3 sessions. So the first one is maybe the most standard situation that we have in chemistry. It is when you have a situation in which you have 4 species which are different, so which are called A1, A2, A3, and A4. And you suppose that you have a reaction which transforms A1 and A3 in A2 and A4. And you also suppose that this reaction is reversible in such a way that you can have also the backwards reaction. And those 2 reactions have rates which are called K1 and K2. And let's say this configuration can be found in a very, very large number of situations. And it is typical of a situation that we will call in the sequel the detailed balance equilibria. So this will be defined probably tomorrow. And I also want to introduce another example, which is a situation in which you have a cycle. So this happens when you have, let's say, 3 different what we will call complexes, and you can go from one of these complexes to the other one only in one direction. So you can turn only in this way. So you have 3 species, A1, A2, and A3. And A1 can react and transform in A2 plus A3. Then this one can become 2A2, and this one can become A1. You should not be frightened by the fact that, for example, here you have A2 plus A3 and here 2A2. So it looks a little impossible, because this just means that maybe you have other species which are here, which are not written, because they are in excess in the solvent in which you have put the species. Okay? So this should not be considered as impossible from the chemical point of view. Okay? And you suppose that you have rates also for this, so let's call them K1, K2, and K3. So this is an example which is which was provided by people working in ODEs, and it's really typical of the situation in which we have the so-called complex balanced equilibria or balanced equilibria. So once again, I will define this a little more precisely tomorrow. So those will be the 2 typical cases that I will present in those 3 lectures. And just let me explain what is a general definition of a network of chemical equations. And I will never use it in the future. It's just to show to you how this generalizes. So the idea is that you consider a set of species which you call A1, AN. So you have a finite number of them. Then you consider a so-called set of complexes. So this is a vocabulary which is used in this theory. A complex means a formal sum with or linear combination with integer numbers of the species which are above. So it looks like something like alpha 1, 1A1 plus up to alpha n, n, a, n. So this is one complex. And then you have, let's say, J complexes of the same form. Sorry, this is AN. And here all the alpha PQ are integer, but they can be equal to 0. Okay? So this corresponds to what you can see here. And this corresponds to what you can see here. Okay? So a complex is typically a linear combination of the species. For real chemical networks coming out of chemistry, what happens is that before in front of an arrow, usually you have 1, 2, or at most 3 species. So that in practice, in those things, typically you have only 3 of the coefficients here which are different from 0. And let's say the sum of them should be less than 3. What you can get after the arrow, in some sense, can be a little bigger, because you can have some kind of, let's say, fragmentation of different species. So you can have things which are a little much bigger, but still you do not, in most of the situations, go beyond 3 or 4 alpha I, which are different from 0. But from the mathematical point of view, the people who have been interested in this theory, and especially the specialists of ODEs who have been working on this, they really wanted to have all the possibilities. And so they defined things in this way, and they tried to get results for any kind of coefficients here. And finally, you give a set of reactions. So let's call it a set of reactions, which are, let's say, symbolized by the arrows which are here. So those are arrows between complexes, together with a number which is, let's say, a strictly positive real number, which is the rate of the reaction, okay? And which, in principle, you can find, if you look at the book of chemistry, you can find it in the table, okay? Associated to a number strictly positive, which is denoted usually by, let's say, Ki, and I here is going from 1 to yet another number, which we can call capital I. So this is, by definition, a chemical network. So as you can see, there is no reason why the number of species, the number of complexes, and the number of reactions should be equal. So just to give you the numbers corresponding to the two examples. Here, as you can see, you have 4 species, 2 complexes, and 2 reactions. And here you have 3 species, 3 complexes, and 3 reactions. Okay. Okay, so from now on, I will speak only about the 2 examples that I have written down. I will never again look at the general definition. So a large part of the mathematical theory devoted to those things has been written by specialists of continuous dynamical systems, of ODEs. And the way you relate, let's say, such a graph to a system of ODEs is by using the mass action law. And the mass action law tells you the following. It tells you that the rate of a reaction is proportional to the product of the concentrations of the species appearing in front of the reaction to the exponent, the alpha I, which are defined here. Okay, so the rate of reaction is proportional to, let's say, product of AI. So I will, from now on, denote it by small ai to the alpha I P or Q. Let's say from I equal 1 to N, where AI is the concentration of the species capital AI. Alpha I Q is the number in the complex Q, which is a complex appearing in the reactants. To the reactants in the chemical reaction, in the considered chemical reaction. That is, the rate of the reaction depends only on the products, on the products that you put inside the solvent. It does not depend on the products which are obtained after the reaction. Okay? And the coefficient of proportionality is exactly this number ki, which is defined in the complex. Okay, so the coefficient of proportionality is ki. Okay, so this is a long sentence to tell something which is very easy to explain. That is, if you look at the reaction in this direction, then the rate of the reaction will just be proportional to A1 times A3. That is, it will be K1 times A1 times A3 here. Okay? If you start from here and you go there, the rate of the reaction will just be K3 times A2 to the square. Okay? So let's write down the ODEs corresponding to the two examples which have been written on the board. So let's call it this one the first example, and this one the second example. So for the first example, the ODE will be written in this way. So we call A1 dot the derivative with respect to time of the concentration A1. And as you can see, you can produce A1 out of A2 and A4 with a rate K2. So you will have K2, A2, A4. But you can also destroy A1 because of the reaction which transfers A1 and A3 to A2 and A4. So you have to remove minus K1, A1, A3. Okay? And of course, A3 is completely exchangeable with A1, so you will get exactly the same ODE, so like this. And now if you look at the equation for A2 and A4, you can see that it's exactly the same, except that you have to reverse the signs, because you are looking at the possibility of getting A2 out of A1, A3, and of losing A2 out of A2 and A4. So the equation for A2 is exactly the same, except that you have a minus sign in front. And the same for A4. You can immediately see that you have a very specific system of ODEs in which all the right-hand sides are equal up to the sign. Okay? So it's, let's say, it has a structure which is very, very different from a random system of ODEs that you would write. Okay? Let's write now the system corresponding to the second example. So in the second example, you can start to see how it works for A1. As you can see, A1 will disappear with a rate K1. So you will have to put minus K1 A1 in the ODEs. And it can be produced out of 2A2, so you will have to add K3 A2 square. Okay? So the first equation is A1 dot is minus K1 A1 plus K3 A2 square. Okay? The situation is a little more intricate for A2, so let's do it at the end. Let's look first at A3. So for A3, you can produce it out of A1, and you can destroy it out of the reaction A2 plus A3 gives 2A2. So A3 dot is just K1 A1 minus K2 A2 A3. Just check. Yeah, okay. And so for A2, one has to be a little more careful because A2 appears in two different places. So first, you can see that you can produce A2 out of A1. So you get K1 A1. Then you can destroy A2 because of the reaction which is here. But you have to remember that when you go from here to here, you destroy two A2s. Okay, so you have to remove minus 2 A2 square times K3. Okay. So you have, this is a big difference with what you have here. It's just not the signs which are changed, but also the numbers in front. And finally, you have to take into account the possibility to go from here to here. And as you can see, what happens when you go from here to here is that you gain one A2. You start from 1, you get 2. And so you have to add K2 times A2, A3. Okay, so let me check. Yeah, that's it. So the point here is, once again, you have a structure which is very specific. As you can see, there are 3 types of terms in the ODE system. You have terms which are linear with respect to A1, you have terms which are quadratic with respect to A2, and you have terms which are quadratic with respect to A2, A3. And of course, all those terms correspond to a different reaction in this cycle, okay? So, this is what you can find in chemistry books. Now in the sequel, I will systematically take for the reaction rates Ki is equal to 1, because it doesn't change at all the mathematical structure. But in principle, we could do everything with the different Ki. You would just get bigger formulas, okay? So for the rest of the talk, but actually this is without loss of generality, we take Ki is equal to 1. And moreover, for the first example, I will systematically use a sort of shortened notation in which I will just use the fact that you have exactly the same right-hand side up to the sign. So one way to write it is just to say that AI dot is equal to -1 to the I times A1, A3 minus A2, A4. Okay, and this is for I going from 1 to 4. And this is a shortened notation for just the system which is here when all the Ki are equal to 1. Okay? And so for the second example, unfortunately, it's not possible to have such a shortened situation, but I will at least remove the Ki from the system. And so we will write things like this. Okay, and let me end this presentation part of the talk by saying that there are conserved quantities related to those systems, and each system has its set of conserved quantities, and the number of conserved quantities can be different, so it can go from 0 to the total, to the number of species of the set. And in the examples that we have chosen, it's easy to see that if you add A1 and A2, you get that A1 plus A2 dot is equal to 0, so A1 plus A2 is conserved. You have the same for A1 plus A4, and you have the same for A2 plus A3. And then it's rather clear that any other combination is just a linear combination of those 3 ones. And so you have 3 conservation laws for the set which is here. So in the first example, we have 3 conservation laws, which are A1 of t plus A2 of t is equal to A1 of 0 plus A2 of 0, which I will call in the future capital M1. So I will systematically take it strictly positive. Yeah. Sure. So the definition that you find in the books on this theory are that they must be linear. I agree with you that in principle you could imagine something else. So you have the same for A1 plus A4, and the last one, let's say, the last one which is independent of the previous ones is this one. Well, let's say that we take it non-negative, in practice rather strictly positive. But anyway, it's then quite clear that taking this into account and using it in the system here, you can end up with only one ODE. And so you can get a sort of semi-explicit solution rather easily for this specific system of ODE, so that the treatment, let's say, of the mathematical treatment of this system is extremely easy. Okay. In the second example, there is actually only one conservation law. And you can more or less guess how you will get it. You see that the only way to remove A2, A3 is by adding the second and the third one. Okay? So if you do that, you end up with terms with A1 and A2 squares. And then you have to add a certain number times the first one in order to try to eliminate those things. Since you have two A1, once you add A2 and A3, you get two A1. The only way to get something is to add 2 times A1 dot. Okay? Yeah. Sorry. Here I forgot. Here, okay. Of course, that will help too when we do the conservation law. And then you see that the only possibility is just to consider 2A1 plus A2 plus A3 and to check that this is indeed conserved. So this quantity is equal to the same quantity at time 0 that we will call capital N. It will take non-negative. And as you can see, you can replace, let's say, A2 or A3 by the value which is taken out from here. And you will end up with a system of 2 ODEs, which in some sense is the last size in which it's very easy to do the large time behavior study by using a phase space, let's say, diagram. Okay. So for both the examples that I have written down, let's say the study from the point of view of dynamical systems consisting of ODEs is something which is very easy to do and which has been known for, let's say, forever. Now, the people who have been interested in this business, in dynamical systems, let's say their main purpose is to try to understand if, when you look now at a completely general chemical network, which is given by this, you can guess the large time behavior of the system. And let's say that they have a certain number of conjectures, and there is one main conjecture which seemingly has been proven in 2017, and which is currently checked, let's say, by the specialist of the domain. I will say a few more words about this when I will speak of the large time behavior of the equations I want to write down. But of course, I'm not a specialist of ODEs, and so I'm not really interested in this, in going in this direction. And my interest has rather been in trying to see what can be said at the level of PDEs for these chemical equations. And if you want to do it at the level of PDEs, of course, you will first look at cases which are trivial from the point of view of ODEs, and try to see if you can already say something at the level of PDEs. So it's the reason why I will present those two things, which at the level of ODEs are really very elementary. Okay. So what are the PDEs which are related to these equations? Actually, it's not such an easy. There is no easy answer to this question. It really depends on the type of situations you are looking at. And for example, if you are looking at gases, what you should write down is rather, let's say, compressible Navier-Stokes or compressible Euler equations for all the species. So you would end up with a large a system with many unknowns, which is basically the system of, let's say, compressible Navier-Stokes for mixtures, for example, in this setting. However, if you are looking at liquids, then there is at least one situation in which the PDEs will be rather simple. It's a situation in which you have a solvent, usually water, let's say, which is in excess with respect to the species, and let's say all those species are just traces in the solvent. Then typically what you would expect is that each molecule will follow a Brownian motion inside the reactor because of the collisions on the molecules of the solvent. And then you will add to this process the possibility of going through the reactions, and you expect to end with reaction-diffusion equations. Okay? I should add at this level that you can, let's say in this talk, I will not speak at all about the rigorous derivation from other models, let's say models with a finite number of particles, or models of Boltzmann type for those things. I will write down directly the reaction-diffusion equations, but you can believe me that, at least at the formal level, it's really possible to go, for example, from Boltzmann equations for a mixture in a certain limit towards the reaction-diffusion equation that I will write down. If you start from particles, I'm not a specialist about this, but I'm sure that, for example, you have in the works of Presutti, for example, you can find a certain number of results. However, and we will see why, I think already today, I don't think that it's really easy to show rigorously the convergence of a model of particles towards a reaction-diffusion model, for example, in this system, because the kind of solutions that we have for this system in general is not strong enough to enable this. So, okay, I will say that. I will come back to this point when we know a little more about the mathematical theory of existence for the systems I will write down now. Maybe I should say first that we are writing systems for concentrations, and so we expect to have non-negative solutions. And at the level of the ODEs, I think it is really quite clear that both this system and this system preserves positivity of the concentrations, since, as you can see, in all terms which have a minus in front, you have, let's say, the species corresponding to the species which is evolving, okay? So for the first one, you have minus A1. For the second one, you have minus A2, etc., and the same for the other one. So at the mathematical level, it's very easy to show that positivity is preserved for the ODEs. So of course, the same point will appear when we write down the system of PDEs. Okay, so let's now write down the systems of reaction diffusion for chemical networks. So the first example, the one which is written here, will be now written in this new setting in the following way. So now AI will be a function of both t and x. It will be a non-negative function, and x will live in omega, which is, let's say, the reactor in which the chemical process is considered. And this will always be a subset of Rn, which will be supposed smooth, bounded, and open, if you wish. And AI will satisfy a reaction diffusion equation in which we take into account the Brownian motion for the molecules of the species AI in this way. So di will be a strictly positive constant here. And I will keep the reaction term minus 1 to the I times A1, A3 minus A2, A4. Okay? And since I have considered a bounded domain, I will add a boundary conditions which is coherent with the, let's say, heat equation part of the reaction diffusion equation. And typically, if you want to maintain at the level of the PDE the conservation laws, you want to conserve all the molecules inside your reactor, and so you impose homogeneous Neumann boundary condition at the boundary. So you would impose this, n being the unit normal vector at the boundary. So that is the set of reaction diffusion equations that we have for the first example. Here, one very important feature is that the DI are different for each I. And this is coming from the fact that there is no reason why the species should diffuse in the solvent with the same diffusion rate. Indeed, you can imagine that the different species have different masses, but in practice they can also have different shapes, and then each has its own diffusion rate. So in the sequel, I will systematically suppose that the DI are strictly positive, but they need not be equal. Okay? As we will see, it's quite interesting also to consider cases in which some of the species are diffusing and some are not diffusing. So it's not completely absurd to suppose that this can be, let's say, also equal to 0, at least for certain species. And this is a situation that you can find, for example, when you have one species which is huge in size with respect to the other species. So like, for example, I don't know, if you are looking at the diffusion of hexafluoride of uranium, you have something, a molecule which is really huge, and this will diffuse in gases which are very light. And so in that situation, you can imagine that you can suppose that one of the DI is equal to 0. Okay. Well, anyway, this is what we will be looking at in the rest of the talk. And so for the second example, we will suppose exactly the same. So we will end up with the equations dt A1 minus d1 Laplacian A1 is equal to minus A1 plus A2 square. dt A2 minus d2 Laplacian A2 is equal to, so A1 minus 2 A2 square plus A2 A3. And dt A3 minus d3 Laplacian A3 is equal to A1 minus A2 A3. So this is a reaction diffusion system corresponding to the second example, and we still add the homogeneous Neumann boundary condition at the boundary. And of course, we will systematically take AI of 0 and x non-negative, since we want to study the evolution of concentrations. Let me briefly say that at the formal level, it's quite easy to see that the non-negativity is preserved by the flow of those equations, since we already saw that the reaction part is preserving this non-negativity. And as far as the diffusion part is concerned, of course, this is just the heat equation, and so you preserve positivity or non-negativity, let's say, when time evolves, okay? So formally, it's clear that the concentrations will remain positive in the evolution. Now I would like to write down what becomes of the conservation laws which have been written on the right-hand side of the blackboard. So let's start with the first example. So now there are two ways of writing them. Let's say we can write them locally or globally. Let's start locally. So locally, I will just write down things in this way. Okay, so this just comes from adding the first and the second equation here. Okay, I just use that the sign is different. And of course, you can do the same for the other quantities. So let's say for these quantities here. And here you see that when we write things in this way, the fact that the DI are not equal does not enable to get equations for a certain quantity at this level. Of course, if the DI are equal, then you get that all those quantities are satisfying a heat equation, and then in some sense you can compute a priori all those quantities and reinject them in the system, and then you end up with only one reaction diffusion equation that you can solve thanks to the usual theory of systems of only one reaction diffusion equation, okay? But if the di are different, of course, you cannot do that, and you don't have this simplification anymore, and you still keep a system of 4 equations. You cannot transform it in a system of 1 equation only. Okay? Now, if you just integrate this on omega, and using the Neumann boundary condition, you will end up with, so this is just by integrating on omega, you will end up with the fact that those quantities are equal to the same at time 0. So this is at time t, let's say. And you have the same at time 0. And I still denote here M1, M2, and M3 those quantities. So like here. And in order for things to be completely coherent, I will systematically suppose that omega has a Lebesgue measure which is equal to 1 in such a way that when I integrate on omega, I really take just the average of the quantity, okay? And it will make the formulas a little simpler. And of course, this is without loss of generality. Okay, so this is for the first example. And for the second example, you can only use the one conservation law that you have. And so you write it in 2 different ways. First, locally. So you have that this quantity is equal to 0. And by integrating on omega, you get that this quantity at time t is equal to the same quantity at time 0, which I call m. Okay? So at this point, we have the complete elementary theory of the system. That is, this is something that can be, in some sense, extended to any kind of systems of this form. We have that non-negativity is preserved in the evolution, and we have a certain number of conservation laws. And when everything goes well, and it's not always the case, by looking at the conservation laws in integral form, you get the totality of the AI inside one of the integrals. So like here, for example, you have the 3 of them inside the integral. And here, at each time, you have only 2 of them. But if you look at the totality, all of them are inside one of the integrals. Since all the AI are non-negative, you get that you have an immediate bound, an immediate a priori bound for the system, which is that in all cases, AI lives in L infinity in time with value in L1 in X. Okay? So this is an estimate that you get immediately because of the conservation laws. Okay? However, you can immediately see that this estimate is not really useful in order to treat the equations, because the typical situation is that you have quadratic terms inside the equations. Like here, let's say A1, A3, or like here, let's say A2, A3. And so, and I would say that this is extremely general in the sense that in most of the chemical networks coming out of chemistry, you have quadratic terms, and usually not cubic terms because of the mass action law. Basically, the probability that you have 3 molecules at the same place is very small in front of all the rest. So usually you have rather quadratic terms. But except in a very small set of chemical networks, you have quadratic terms. You do not have only linear terms, okay? And so the basic estimate that you need is that the AI are in L2, okay? You need AI to be in L2 in order to give a sense to the right-hand side, okay? Let's say if you're not able to show that, then the only possibility that you have is to try to use renormalized solutions, which were introduced by D'Epernay and Lyons at the end of the 80s for the Boltzmann equation, which has a structure which is anyway quite reminiscent of this, that is a quadratic term, and an L1, L infinity estimate, L infinity L1 estimate, I mean, which is obvious because of the conservation of mass. And in the case of the Boltzmann equation, we know that it's not possible to get an L2 estimate in all the variables except in perturbative situations, let's say. But in general, it's not possible to get it, or at least it has not been possible up to now to get it. The situation here is much better with respect to the Boltzmann equation, basically because instead of having an advection operator, we have the heat equation in the right-hand side of the equation. And so there is, of course, more hope to get estimates out of the heat equation than starting from a hyperbolic style operator, okay? And in fact, the general L2 estimate, let's say, for cases in which you have all species inside one of the integrals coming out of the conservation laws. So it was obtained in the early 80s by Michel Pierre and Didier Schmidt. And I want now to explain how it works, because this is really the main tool for getting existence of weak or strong solutions for those equations. So this is sometimes called the duality lemmas. So I will maybe write down the lemma and then explain how it can be used in the cases we are interested in. So the main lemma says the following. Suppose that you take a function mu which depends on t and x, such that mu is bounded above and below by strictly positive constants. So suppose you have a situation like this. And here, x is living in a set omega, which is, as usual, an open, smooth, bounded subset of Rn. And now imagine that you have u, function of t and x, be a solution of a parabolic equation in which mu is the coefficient of the parabolic equation, but with respect to what is usually seen in the literature, you suppose that mu is inside the Laplacian and not between the divergence and the gradient, okay? So this is a situation which is maybe a little less standard than what is usually considered in the literature. And suppose also that you have the homogeneous Neumann boundary condition, which is in this case writes like this. Okay? So imagine that you have a parabolic equation like this. What the duality lemma tells you is that then there exists a constant Ct, and actually we will see, sort of compute this constant in the sequel, which is strictly positive and which depends on the time capital T on which you are looking at the equation, such that the integral of u square, so this is an integral which is taken both in time and space. So this quantity here is bounded by Ct times 1 plus the same quantity for the initial datum. So the L2 norm of u at time 0 to the square. And Ct actually depends only on delta 0 and d0. So maybe we can write it this way. Okay. It does not depend on mu except through the upper and lower bound of mu. Now this lemma looks very strange because the point is that since mu is inside the Laplacian, basically it's as if, for example, you try to put it between the divergence and the gradient, you will have, in some sense, to take the derivative of mu, and you don't suppose anything on the derivatives of mu. Okay? You just suppose that mu is bounded above and below. So it's very strange that by satisfying an equation which is so weak, with something that we cannot, for which you cannot take derivatives, which is inside the Laplacian, that you could get anything at the end. Okay? So though the proof of this is quite easy, and we will see it, it will take like 10 minutes to get it, it's not really surprising that this was discovered rather late. So this was written down in this form by Michel Pierre and Didier Schmidt around the beginning of the 80s. So actually, the proof is almost completely contained in the word duality, which is here. And it consists in saying basically the following thing. We don't know anything about parabolic equations in which the coefficient is inside the Laplacian, but we know a certain number of things for the same equation when it is outside of the Laplacian. And when it is outside of the Laplacian, we just get actually the dual equation in the usual L2 sense. So let's try to use what we know about the duality, the dual equations for this. Okay? So let me show you quickly the proof. I will not really write all the details of the proof, okay? This is more a sketch of the proof, but you will get really the main estimates here. So the idea is to use a multiplicator here, which is a solution of the dual problem. So let's define a function v of t and x such that minus dtv minus mu of tx Laplacian V is equal to U. So let's say we suppose that U is given, and we built this parabolic problem in which we solve the equation which is here in terms of V. We add the Neumann boundary condition for V, and in order to be able to solve the reverse reverse parabolic equation with a mu which is positive, we can only go backwards, okay? And so we have to impose V at time t, and for this we take 0. And V will be defined between 0 and capital T, okay? This is exactly the dual problem in the L2 sense, in the Hilbert sense, corresponding to this, okay? So the reason why you introduce this and we take as a source the U, which is there, is that if now you multiply this equation here by V and you integrate by parts, what you will get is the following. So I integrate first V dt U minus V Laplacian of mu U, like this. And this is equal to 0, okay? I integrate in both t and x the equation which is here, once I have multiplied first by v. And then I do the integration by parts. So what I will get is the following. Integrating by parts in time, I will get minus u dtv, and two boundary terms. The one which corresponds to capital T will be equal to 0 because I have taken v at time capital T, which is 0. And then there is a 1 at time 0, and it gives me exactly minus the integral of u at time 0 times v at time 0. Okay? So this is a part which is related to the integration by parts of this quantity here. And then I integrate by parts this one. So since I have a Laplacian here, I will get mu u Laplacian v, like this. And you can believe me when I tell you that the boundary terms will be equal to 0. Actually, there are two boundary terms because you integrate 2 times. And they will be equal to 0 thanks to the 2 Neumann boundary conditions, the one on v and the one on u. So each of them enables to cancel one of the boundary terms. Okay? So you end up with this. And of course, v has been built in such a way that minus dtv minus mu Laplacian v is exactly equal to u. Okay? So what you get is that this is equal to minus u square. Let me check the signs. No, the sign is plus. Okay? Yes. I put on purpose minus here, so the sign is plus. Well, anyway, what you see is that at the end of the day, if you want to know that this quantity is finite, you just have to prove now that this quantity is finite. Okay? Since this is what you want to prove, now we have to work on this quantity here. But this quantity is made of the product, or if you want, the scalar product in L2, of the initial datum for u, which let's say is given. So it will appear, of course, at the end. So this we don't really care. And the value at time 0 of v. Okay? So the whole point now is to try to show that the value at time 0 of V lies in L2 of omega. Okay? And for this, we can start from the equation here, which has the mu outside of the Laplacian, and so for which, therefore, we have a certain number of techniques which allow to get estimates for V. Okay? So, let's now call this. So remember that this is equal to 0, okay? Let's call this star, and we keep it somewhere. And now we try to show something on V at time 0. We start from here, and we say, well, the easiest thing to do when you have a parabolic equation with a coefficient outside of the Laplacian is to multiply by the Laplacian itself and to integrate by parts. So let's try to do this. We know that minus Laplacian V dtV minus mu Laplacian V to the square is equal to u Laplacian V. I've just multiplied by Laplacian V. And now I integrate this on both time and space. Okay? So this term is okay because it already has a sign. Okay? So this is minus something to the square. And the term which is here looks ugly because you have various derivatives inside, but actually, if you do the integration by parts in x, you will get here a gradient and here dt of the gradient. So this will just be dt of the square of the gradient divided by 2. And now if you integrate with respect to time, you will get the gradient of v at time t minus the gradient of v at time 0. But v is 0 at time t, so at the end you get just the gradient of v at time 0. So the term which is here, after integration by parts, it just gives you this up to the sign. And still I'm lazy. I will just have a look. Yes, so it's plus if you now change the sign here. So what you will get is the following. I change the signs in order for it to be okay. Okay. The important point, of course, is that you have two non-negative terms on the left-hand side here. So we are still far away from knowing what is v at time 0, but actually we'll be going in the right direction because you can see that by using Young's inequality, it will be possible to, let's say, estimate this term by this term here, provided that mu does not go to 0. But this is exactly the hypothesis which is here, that mu is bigger than delta 0. So let's say, now if I say that this one is bigger than delta 0, let's write it this way. And for this one, I use Young's inequality to tell that this is less than, let's say, delta 0 over 2 times the Laplacian to the square plus 1 over 2 delta 0. Let me write it here. Times the integral of u squared. Okay? And in this way, I can absorb this term in this one up to paying a price which is just u squared. If I put all of this in a nice framework, what I get is exactly that I now have an estimate for the square of the Laplacian of V. And this estimate is exactly that this quantity is bounded by the L2 norm to the square of U multiplied by 1 over delta 0 square. Okay? So I know something about the Laplacian of V. How can I relate V at time 0 with the Laplacian on V of V for all times, integrated like this in time? Well, the best way to do it is just to say that V at time 0 is just the integral between 0 and t of the derivative of V up to the sign, okay? Because we already know that V at time capital T is equal to 0. So I can relate this to the derivative in time of V. But then the equation tells me that the derivative in time of V can itself be related to the Laplacian of V, okay? So I can relate this to this. So let's try maybe to do it seriously. So what I say is the following now. V at time 0 is just the integral, let's say minus the integral from 0 to t of dtv at time t dt, like this, okay? And now I use the equation, minus dtv is just mu Laplacian v plus u. And what I want to estimate is the L2 norm of this quantity. So I take the square and I take the integral. Like this. And I say that this is okay, this is equal to this quantity. And now, as you can see, I just have to use Cauchy-Schwarz in order to get the integral here outside of the square. So by Cauchy-Schwarz, this is less than actually t times the integral on omega t of mu Laplacian v plus u to the square. Sorry, I have some doubt, but no, I think it's okay. I think it's okay. And now I will just say that this is less than 2t times, so mu square Laplacian v square plus u square, like this. And mu square, by assumption, is less than d0 square, okay? So here I can put actually d0 square. So now I see that this can be estimated by 1 over delta 0 square times the integral of u square. This is already u square. So all in all, what I get is 2t times d0 square divided by delta 0 square plus 1 times the integral of u square. So I was able to estimate the L2 norm of v at time 0 by the L2 norm of u. And as you can see, what will be the ct delta, etc., will be this or the square root of this or the square of this. We will just see now. Okay, so in order to conclude, I now come back to star, and I see that now, thanks to star, the integral of u square is dominated by Cauchy-Schwarz by the integral of u at time 0 square times the integral, so to the 1/2, times the integral of v at time 0 square to the 1/2. And this is, thanks to this computation, less than square root of 2t times 1 plus d0 square, so delta 0 square, times the square root of this. And now I simplify by the square root of u. And finally, I get exactly what is written here. Okay? So I hope that you agree with me that this is a reasonable proof. It takes like just 1/2 of the blackboard to be written down, and 15 minutes, 20 minutes. So if you want to make it, yes. Yes, so here in this version here, I don't really need the 1+. I could write it this way. I cheated a little in the proof by telling you, let's consider V satisfying this. Actually, it's not that obvious that for a given U, let's say, in something, which we don't really know yet that it is in L2, it's known only at the end, you can really find V satisfying this. So actually, at this point, if you want to make it completely rigorous, you have to put here some, let's say, smooth function, which you don't precise yet, to do everything with this smooth function, and then use a duality argument at the end with this smooth function. So one would need like maybe 10 more minutes to make it completely rigorous. Okay? But anyway, this is really the skeleton of the proof, and let's say all variants of the lemma can be obtained by looking at this proof and trying to improve it. So, how is this lemma used in our case? So actually, this is something which is really strange, and in some sense, from my point of view, something which shouldn't work. So there is some kind of miracle, or I would say something even unnatural at this level. Because the way you will use the lemma in the case which is interesting us is the following. Let's look, for example, at the first example. If you look at the local conservation law, you know that dt of a1 plus a2 minus Laplacian of d1 a1 plus d2 a2 is equal to 0. Okay? Now, from this, in principle, you should not extract anything. This is not an equation. Those two quantities have nothing to do one with the other. So in some sense, you should forget about this and just use the fact that by integrating in x, you get a real conservation law, which gives you an L infinity in time, L1 in x estimate. However, I think the magnificent idea of Michel Pierre and Didier Schmidt was to say that you can, in some sense, write this as an equation by enforcing a1 plus a2 inside, so like this. Okay? Now, this should not work. I mean, That looks crazy. I mean, just to impose the equation like this looks really crazy. Actually, it's what works. So you define mu as this quantity here, and it's clear that mu will be living between the maximum of d1, d2, and the minimum of d1, d2. Okay. And so, if you define delta 0 and capital D0 at those quantities, you can use the duality lemma. And what you get is that A1 plus A2 lives in L2 in T, L2 in X. To be precise, it is L2 in T on a given time interval. It's something which does not work for infinite time, since, as you could see in the proof, actually, the dependence with respect to capital T is like square root of T at the end. So the estimate is sort of degenerating when T goes to infinity. And of course, you can do the same can be done for A1 plus A4 and A2 plus A3, so that at the end, you get that AI is living in L2 of T and X. Okay? And this is exactly what you need in order to define a weak solution of the reaction diffusion system, because you have quadratic terms in AI in the right-hand side. Okay? And of course, for the second example, it works exactly the same. This time, you will just write that this quantity is equal to 0. Okay? And with the same argument, you get that 2A1 plus A2 plus A3 lives in L2 in T and X. Now, you can wonder then how this a priori estimate relates to existence theory. So the idea, as usual in PDEs, consists in writing a system, an approximated system for which you already know that you have a solution, and then to pass to the limit in this approximated system in order to recover existence for the system that you want. So let me use the last 5 minutes of the talk for writing down a theorem. So this is a theorem which is due to Clémence Fellner, Michel Pierre, Julien Vauvel, and myself. And this was proven, I think, in 2007. So the theorem says the following. Let omega be an open, smooth, bounded subset of Rn. Take Ui initial in L2 of the variable x, L2 of omega, if you wish. Take di strictly positive. Then there exists a weak solution to the reaction diffusion system dt AI minus di Laplacian AI equal to this. And the boundary, the Neumann boundary condition, plus, of course, the fact that the initial datum is the right one. And this is for I equal from 1 to 4. And so now the proof, I propose a 1-minute proof. So the proof consists in taking AIN, where n is an integer number, such that AIN is satisfying the same equation, except that the right-hand side is saturated by, let's say, the sum 1 plus 1 over n, the sum of AI square. This is a very bad notation. Okay, AIN to the square. And plus Neumann boundary condition plus initial data. Now, this is a bounded right-hand side, and so usual theorems for systems of reaction diffusion equation tells you that there is a smooth solution to this one. And then you just have to let n go to infinity and check that AIN satisfies the right a priori estimate. So the first thing is that to check that for this approximated system, the same a priori estimates are true as for the limiting system, and to use the duality lemma in order to get that AIN is bounded in L2. To be precise, L2 of 0t times omega. Once you know that, you are almost done, because if you know this, this ensures that this quantity is bounded in L1, okay? And so you have a quantity AIN which satisfies the heat equation with a right-hand side in L1, and this ensures that this AIN is compact, let's say, for example, in L2. And so you can pass to the limit in the right-hand side, provided that you get some equi-integrability of the term, let's say, AIN times A3n. So I use the last 30 seconds just to write the right sentence, and then tomorrow we'll see how it's possible to show that this sentence really holds. So one can pass to the limit, provided that, let's say, UIN, UJN is equi-integrable as a sequence for any ij between 1 and 4. And we will see tomorrow how it's possible to get this equi-integrability, since a priori the duality lemma just tells you that UI, UJ is bounded in L1. Okay, you need a little more. Okay, okay, I propose to stop here for today. Mm-hmm. Yes, Herbert.
So unrelated question.
Yeah, sure. So if you have, let's say, low dimension, so let's say dimension 1 or sometimes dimension 2, it's really much easier to do a certain number of things here. And for example, just to give a very, something which can be told in just 10 seconds, is that if you are in dimension 1, you have a heat equation with a right-hand side in L1, so you will get that AIN is bounded in L3 minus 0. So let's say 3 minus epsilon for all epsilon. And so you already get this freely immediately. But actually, it's also possible to get it in dimension 2 by working a little more. This I will try to explain tomorrow. And for dimensions strictly bigger than 2, then the theorem is true, but we cannot add much more to what it's said here, whereas in dimension 1 and 2, it's really possible to show much more. Like, for example, the solutions are strong. Yeah, sure. So that's the point. So this is true in dimension 1 and 2. And actually, so I will maybe tell a little more tomorrow, but now, let's say Goudon and Vasseur claimed a few weeks ago that they know how to do it in any dimension. But it's not really yet on the archive. So this is actually a quite, let's say, interesting topic to know if those weak solutions are actually strong, provided that the initial datum is reasonable, let's say. Mm-hmm. No. So the point is that in the theorem here, you get global solutions, and in dimension 1 and 2, I will tell tomorrow that those global solutions are indeed strong for all time. Mm-hmm. Yes. Yes, let's say, if you want to show it rigorously, let's say I told that it was clear at the formal level. If you want to show it rigorously, the point is that you do it on the regularized system. You do it on this system here, and then you pass to the limit, and of course you get non-negative at the end. So here, once you are at this level here, you can really get it by, let's say, here you have solutions which are really smooth. So you can really look at what happens at a given point and check that you will you will have the right monotonicity, etc., etc. Mm-hmm. Okay, so if, of course, what will happen is the following, actually. So if you suppose that all initial concentrations are 0, of course, it will remain 0 forever. If now you have, if you have at least one of them, which is non-zero almost everywhere, which has a set of non-zero measure on which is strictly positive, then actually for any strictly positive time, all concentrations will be strictly positive and it will stay forever. So this can be proven, let's say, at least, let's say with this level of generality, it can be proven in dimension 1 and 2 because you have good solutions. If you are in dimension strictly bigger than 1 and 2, then the same kind of statement is true, but you have to be a little more careful about what you say because it will be only almost everywhere and things like that.
What part of this is true when di is not constant?
So my feeling is that if di is non-constant, but strictly bigger than a constant, strictly less than a constant, plus, let's say, C2, probably C1 is enough, but let's say C2, then everything goes exactly in the same way. Of course, if you take a di which can have jumps or things like that, then I don't think that it's really possible to do the duality lemma I cannot really answer. I didn't check, but my feeling is that you may have difficulties if the DI have jumps.
The DI are smooth, but can it do you have any guess?
Yes, so actually this is a very interesting situation. I'm not sure that it's really interesting for the existence theory, let's say, in the sense that, well, but for the large time behavior that we will look at in the future, this is very important because, of course, if you have places in which you don't have diffusion, you could imagine that there you have the reaction only, and in some sense, you cannot homogenize what happens. So there, of course, the large time behavior may depend on places in which you have no diffusion at all. But the direction in which people have been looking at is rather the situation in which one of the DI is equal to 0, and let's say the other ones are strictly positive and constant. So this is more the situation which has been looked at. And then with only one DI equal to 0, basically you can reproduce most of what we've been saying here. If two of the DI are equal to 0, you begin to be in trouble, let's say. Of course, with 3, it's even worse. So anyway, the question of the degeneracies of the diffusions is something which is quite interesting and which has also to do with controllability of the parabolic equations. So people doing control theory are also interested in those issues, actually. Mm-hmm.
Talking about generality,
mm-hmm.
Theorem could be extended to all cases in which you have n-1 conserved quantities?
No, so here actually I did not really use very much the conserved quantities. What I used is basically just the fact that all the species are in one of the conservations.
Yes, yeah, that's it. Yeah.
So of course, if you get out of this situation, you cannot use anymore the duality lemma and you're in trouble. But this situation is really very typical. I mean, it's not so easy to find systems in which you have no conservations at all.
Yeah, but what about the second example?
So in the second example, you have 2A1 plus A2 plus A3. So you have only one conservation, but all species are inside. So you get that all those quantities are in L2. They are all positive, okay? So they are all in L2. So it does not depend a lot on the conservation laws. What cannot be extended easily is the type of powers that you have in the right-hand side. Here, it works very well when it's quadratic because you get out of the duality lemma an L2 estimate. But if you have a cubic term, of course, this will not be sufficient.
So it applies directly to the second example?
So yeah, so for the second example, I did not write the theorem, but actually you have the same kind of theorem. But for some reason, which we will see tomorrow, actually the second example is rather better. Is a little better from the point of view of the smoothness theory because it is less symmetric. So what happens here is that for the first example, all the AI plays the same role. And so you cannot select one of them to start and do something then. Whereas in the second example, you can select basically A1, which appears only in linear terms. And so you can say a little more on A1, and then this helps you to build things on A2 and A3. So when it is not so symmetric, usually you can do a little more. But this we will see tomorrow. Anyway, this cannot be extended to all systems of reaction diffusion which would come out of chemical networks. There are clearly limitations, and basically things get more difficult when you increase the number of equations, or of species if you wish, if you increase the dimension, and if you increase the power that you have in the right-hand side. So in all those directions, you have difficulties. The only thing which I think has been proven in wide generality is the existence of renormalized solutions. So this was done by Julian Fischer, whom I think you met in Vienna last year, and who did a very nice work. but which still has one limitation. It is that it looks at situation in which you have basically only one chemical equation, but it can be of arbitrary order, let's say. So. Thank you.